Good evening, friends. Today we would be dealing with a topic called parallel plate capacitor. So last time we have classified capacitors into different types like spherical capacitor, cylindrical capacitor, and parallel plate capacitor. Out of which I said we would be specifically focusing on parallel plate capacitor so far as our syllabus for CBSE as well as HSC is concerned. Okay. So let's understand how a parallel plate capacitor would look like. So before I talk about that, let's have a quick recall. Like a capacitor is a device which would be storing large charge at a very low potential in a circuit. Okay, so it's an energy storing device basically, or we also call it as an arrangement basically, which stores energy or charge basically at very low potential. Now, when we talk about parallel plate capacitor, friends, this is how a parallel plate capacitor would look like. It would consist of two plates which are very near to each other. It's a three-dimensional view, a two-dimensional view in this case. So two plates. Okay, so obviously on one plate it would be plus Q given, and another plate which is close to it in the vicinity of it, separated by a distance small d, minus Q would be induced, and the outer part would be given connected to earth in that case. So these are two conductive plates. Obviously A is the area. A resembles the area, plate area. D stands for the distance between the two plates. And dielectric, either there would be a empty space over here or air over here, or you can fill dielectric to change the capacity of a capacitor. Alright, so this is how a parallel plate capacitor would look like. Now we would be deriving a derivation for parallel plate capacitor, the capacity of a parallel plate capacitor. So let's proceed further then in that case. Please make a note of this diagram before we move ahead. Hopefully you have noted down this diagram for parallel plate capacitor, friends. So we would, for analysis, we would be considering the two-dimensional diagram over here for parallel plate capacitor. So let's proceed further. Yeah, here in this diagram you can see, we all know capacity is given as Q by V. This is what we have defined. Charge stored per unit potential is nothing but the capacity of a capacitor. The unit for capacitance would be farad. So 1 farad will be 1 coulomb divided by 1 volt. We have defined it. And in a circuit, a capacitor would be denoted by this notation. So when we are talking about parallel plate capacitor, friends, so the electric intensity which is generated between the two charge plates, which is always directed from positive charge to negative charge, say for a distance d in this case, would be given by E is equal to sigma upon K epsilon naught as per the Gauss theorem which we have studied, if you all remember, where sigma is the surface charge density, that is charge per unit area. K stands for the dielectric. Now if it is air, then K will be 1. Had it been other material between the two plates, then accordingly you would have substituted the value of K. Epsilon naught stands for the permittivity of free space oblique vacuum or air, you can say. So this is the equation for electric intensity as per Gauss theorem, the application of Gauss theorem. Potential, there is relation between the potential and electric intensity. We have studied that electric intensity is equal to the potential gradient, right? So from that, can I say if E is equal to V by D, V can be substituted as electric intensity multiplied by the distance between the two plates. We have established this relation. We have derived this relation earlier. Now we can substitute the value of electric intensity over here, and electric intensity is given by sigma upon K epsilon naught. So then the equation for potential will become E into D, where E stands for sigma upon K epsilon naught into D, where again I repeat, sigma is surface charge density, that is surface per unit charge per unit area, surface area. K stands for the dielectric. Epsilon naught stands for the permittivity of free space. and small d stands for the distance between the two parallel plates of the parallel plate capacitor. Now, having said that, we get the equation for potential as sigma upon k epsilon naught into d. Now we all know sigma is charge per unit area. That means sigma will be charge divided by area, right? So from that, I can say charge would be equal to, the total charge would be sigma multiplied by area, that is the surface charge density multiplied by area. So I know the value of V, I know the value of Q. As per the concept of capacitance of a capacitor, capacitance is given as Q divided by V. So let's substitute the values of Q and V over here. So when it is Q divided by V, Q stands for sigma into A, whereas V will stand for, E will be equal to sigma upon K epsilon naught into D. So you can see sigma gets cancelled, and ultimately K epsilon naught and area, they go in the numerator divided by D. This is the equation for capacitance of a parallel plate capacitor. So directly if you observe friends, here in this case, C will be dependent on dielectric. Higher the value of dielectric between the two plates, higher would be the capacitance. Second, if the area is large, then the capacitance would be more. If the distance between the two plates is less, then the capacitance would be more. This is how you're supposed to analyze it. So please make a note of this, friends, before we move ahead, we proceed further. So this is the derivation for equation of capacity of a parallel plate capacitor and the factors on which the capacitance would depend. Okay, hopefully you have noted this down. Let's proceed further then. This was the general equation which we have derived. Okay, these were the steps which we followed to get the equation for capacitance. And finally, we got the equation for capacitance as K epsilon naught A. Here K stands for 1 over here, therefore, but or else the general equation would have been C equal to K epsilon naught A by D, where epsilon naught, you all know, it's electrostatic constant, permittivity of free space. C stands for capacitance, A stands for area, and D stands for distance between the two plates. Please make a note of this slide. So from this, you can come to a conclusion how to increase the capacitance. Obviously, by increasing dielectric, by increasing area of the plates, how, and by decreasing the distance. And if you want to decrease it, vice versa. Hopefully, you have noted this down, friends. Let's move ahead then. Yeah, here epsilon stands for permittivity of free space, and this is the value for it. 8.8542 into 10 raised to minus 2 Coulomb square per Newton meter square. Let's proceed further.
Sir,
Yes.
can you go back to the previous slide? The
Yeah,
one.
this one you mean to say? Is this the slide which you are waiting for? Asking for? If you are done with it, let us know. Okay, should I consider it as done?
Yes, sir.
Okay. Yeah, I was talking about the units now for this particular formula. Now here, Coulomb, capacitance would be given by the unit farad. Okay, epsilon, the unit is Coulomb square per Newton meter square. Okay, this C stands for Coulomb, this C stands for capacitance. That's the difference. Okay. Obviously, area unit is meter square, distance is meter. So when you all substitute this and simplify it, let's see what format we get. Okay. Okay, hopefully you have noted this down. Let's proceed further. Yeah, so when you put the value, say farad would be then given as, put all the units over here and then try to simplify things. It would be easier for you to define 1 farad then in that case. Okay, maybe I believe you have noted this down. Let's move ahead then. So if you simplify this, it will be simply Coulomb square per Newton meter. So Newton meter can also be substituted as Newton meter square and meter, in fact not meter square. It can be substituted as joule. Coulomb square per joule is farad in a way. Okay, hopefully noted down. Now let's try to understand how big would be 1 farad. Okay, say for example, if capacitance has to be 1 farad, let's see what would be the area of the plate. Okay, we'll put all the values as unity over here. Okay, say we put the value for epsilon naught in its general value of epsilon naught, d as 1 meter. Then in that case, the area comes out to be how much? You can see 1.1 into 10 raised to 8 meters square. That means a square sheet 10 kilometer long would constitute what is called as 1 farad. This is how 1 farad would be. So this is how you can understand what 1 farad can be. Okay, fine. So we will move ahead towards the next slide where we were connecting these capacitors in different combinations where we lost connection last time. Okay, so let's talk about them briefly. Okay, before we move ahead. Yeah, so whenever we can connect them in two ways. The capacitors can be connected in two ways. One would be the series combination and the second would be the parallel combination. Now in series combination, we all know whatever current flows through the devices would remain same. That means the charge across every capacitor would be same, but the potential would get distributed. Here in case of parallel combination, the potential will remain same, but the charge will get distributed along the three branches. Okay, so based on that, we will try to analyze the situation. So when it comes to series combination, friends, you can see charge is same on every capacitor, C1, C2 and C3. All right. V gets divided into three parts, V1, V2 and V3. So we can use a general equation where V would be equal to V1 plus V2 plus V3 for three capacitors. Had it been n number of capacitors, you could have generalized it for n. But then let's get back to the basics. Okay, we all know C is given by Q by V. So from this, can we say V is equal to Q divided by C? Then subsequently, I can say V1 would be equal to Q by C1, V2 would be Q by C2, and V3 will be Q by C3. So I know the values of V, V1, V2, V3. I will just substitute it over here in this equation. For V, I will substitute it as Q by C. For V1, it would be Q by C1. For V2, it would be Q by C2. And for V3, it will be Q by C3. So throughout, you can see the charge Q will get cancelled out. So ultimately, you get the equation for the series combination as 1 by C equal to 1 by C1 plus 1 by C2 plus 1 by C3. Had there been n number of capacitors, you could have generalized it for n number. But then this formula tells us that, if you connect the capacitors in series, the resultant capacity would decrease. So whenever you want to decrease the capacity of a circuit as per the requirement or as per the design, then we would go for series combination of capacitors there. Please make a note of this slide. Hopefully you have noted this down, friends. Let's move ahead then. The second type of combination which I was talking about was parallel combination. Now in parallel combination, you can see The charges get distributed as Q1, Q2, Q3 across the capacitors C1, C2, C3. But the potential will remain same. So as per the law of conservation of charge, I can say Q gets divided into Q1, Q2, Q3. So I can state an equation over here, that is Q equal to Q1 plus Q2 plus Q3. Okay, now we have a general equation. Capacity or capacitance would be Q by V. So Q can be shuffled as C into V. Subsequently, Q1 would be written as C1 into V. Q2 would be written as C2 into V, and Q3 would be C3 into V. So now I know the values of Q, Q1, Q2, and Q3. I'll just substitute it in this equation. So instead of Q, it is CV. Q1, it is C1V. Q2, it is C2V. Q3, it is C3V. So throughout you can see V gets cancelled out. So ultimately for parallel combination, you get the equation as C equal to C1 plus C2 plus C3. Okay, so had it been n number of capacitors in parallel, you just generalize it for n numbers. So in a way, this equation tells you when you connect the capacitors in parallel, the resultant capacity increases. So whenever you want to increase the capacity in a circuit as per the design, connect them in parallel. These formulas for series and parallel combination of capacitors, they are exactly opposite to that of resistors. If you can just try to recall that or trace it. Exactly opposite. Whatever was the formula for parallel for capacitor, it would be the formula for series for the resistors and vice versa. So always you should remember, okay, the difference between the two applications over here. Please make a note of it so that we proceed further. Yeah. Hopefully, I believe you have noted this down. Let's proceed further then, friends. Yeah, you can have a generalized slide where you can just mention all the formulas throughout together. So everything is being worked out over here, okay? For series, what the formula would be for capacitors. Similarly, we have derived it for parallel. We have derived the equation for capacitance for a parallel plate capacitor. We have mentioned what 1 farad would be. This is something which we have not derived, but we subsequently will be deriving it, okay? Energy in this capacitor. It is either given by this formula of CV square Q square by 2C or QV by 2. We would be deriving this derivation subsequently. So please make a note of this before we proceed further, solve some problems or to identify different types of problems which may come under these topics. Okay, I believe you have noted this down. So we move further. Let's proceed. So typical type of problems which you may come across. Okay, so how to depict this? Okay, if you come across a combination like this, so see 1 and 2 constitutes one capacitor. Okay, 3 and 2 will constitute another, and 3 and 4 will constitute. That means these are three capacitors in parallel. This is how you're supposed to depict the combinations. Okay. Normally, whatever rules, Kirchhoff's rules you have applied for resistors, you can also apply them to solve the capacitors in steady state. Okay. So please make a note of this before we move ahead. This is just a slide to give you an indication like how you depict things, how you consider them in series and parallel. Okay. Let's move ahead then. Okay. Here comes the question for you people. Calculate the capacitance of a parallel plate capacitor whose plates have an area of 0.525 meter square and are separated by a distance of 2.15 mm. Just now we have derived this equation for capacitance of a parallel plate capacitor, and the equation was K epsilon naught A by D. K is 1 over here. If not given, that means you have to consider it as 1. You have to consider air between the two plates. Epsilon naught is known to us, and we all know area is also given to us. We just substitute the value for epsilon naught. It is 8.85 into 10 raised to minus 12 with the corresponding unit multiplied by area given to us is 0.525. Okay, it's a total area of both the plates, so no need to multiply it by 2. Just check out the wordings of the problems. Okay, and then distance between the two plates, convert it into meters, so 2.15 into 10 raised to minus 3. You solve this, you get the capacitance as 2.16 into 10 raised to minus 9 farad. So you may get straightforward questions, and then the trick can start with this here onwards. Okay, please make a note of it before we proceed towards the next level problems. Yeah, I believe you have noted this down. So let's proceed further. Now here in this case, the parallel plates of the capacitor are given, the dimensions are given 5 into 10 centimeter. The separation between them, that means small d is given 2 centimeter. And the dielectric they say is not 1 here, they have filled it with bakelite. And the dielectric they say is 4.7. Then work out the resultant capacitance. Now the formula would be the same, you can see. But here K is given to you as 4.7. And area, you can see area will be 5 into 1. Okay, so these are the dimensions given, so convert it into meter square in that case. All right, when you convert it into meter square, convert distance also, small d also in meter. You solve it, you place it, then in that case you get the capacitance as 1.04 into 10 raised to minus 11 farad. So that can be a change, okay, where they give you the value of dielectric. Other way around, they may give you everything. They may give you the capacitance. They may ask you the area. They may give you everything. Only D is unknown. They may ask you the distance between the two plates. Or everything is given and they may not be giving you the dielectric. They may ask you to work out the dielectric and so on. So these permutations and combinations are always possible with the problems under this category. So please make a note of it before we proceed further. Okay, I believe you are done with it, friends. So let's move ahead. Okay, let's talk about the series capacitors and the charge voltage problems on this. Okay, first thing is specifically series. Okay, so we all know what formulas we apply when it comes to series capacitors. So here is the problem given to you. They say C1, C2 and C3 with the corresponding values 12 farad, 6 farad and 5 farad. They're connected in series. The battery voltage is 6 volt. Now the questions they are asking, what is the total voltage gain in the circuit? What is the total capacitance of the circuit? What is the total charge stored in the circuit? Okay, total capacitance will be directly given by the formula which we have derived. Then the question extends, what is the charge stored on each capacitor? Then what is the voltage across each capacitor? So all these things are to be worked out. So please make a note of this problem, and subsequently we will try solving this problem. Okay, I believe you have noted down this problem. So we will try to answer these questions with the help of the concepts which we have studied. So the first point is about total voltage gain. So total voltage gain, they say directly it's visible over here, 6 volt. Total capacitance, you can work it out as 1 by C1 plus 1 by C2 plus 1 by C3 and then the reciprocal of that. So ultimately it will amount to, you can see, reciprocal of this, right? So 2.22 farad. When you solve it, you will get these answers. Okay, so this was the second part of the question. The third part was, what is the total charge stored? So by the basics, we know Q total will be total capacitance multiplied by total voltage. The total capacitance we have worked out 2.22 farad. Total voltage we all know it's 6 volt. So multiplied by 6 volt. This is the total charge. Okay. So QT. So 13.32 coulomb. Now whatever is the total charge, because it's a series connection, it will be same for C1, C2 and C3 if you all remember. So individual charges also would be equal to 13.32 coulomb because it is a series connection. Please make a note of this slide so that we move forward to answer the remaining questions. Okay, I believe you have noted down this answer 3. Now the fourth question was the individual charge on every capacitor. Because it is in series, I said that whatever is the total charge would be the same charge across each capacitor. You can see. So what is the charge stored on each capacitor? So Q total will be equal to Q1, Q2 and Q3. They all are same. So ultimately the value for Q1, Q2, Q3 in that case would be 13.32 coulomb only. Okay, this was the fourth part of the question. So we got the answer to this. Now when it comes to total potential across each capacitor, obviously that will be different. So we have to work out the total potential in the fifth part. So please make a note of this answer first. Then we will try working out for the fifth part of the question. Okay, I believe you have noted this down. Okay, let's proceed. Yeah. Now the fifth question, they said, what is the voltage across each capacitor? Obviously that would be different because it's a series connection. So C1, here total voltage will be V1 plus V2 plus V3. Okay, and we know the basic formula Q equal to C into V. So from this, V1 can be written as Q1 by C1. So Q1 is 13.32. We have worked out. Whatever is the total will be the same charge on each capacitor. And C1 is 12 farad. So when you divide it, you get this as 1.11 volt. Similarly, V2 would be Q2 by C2. Q2 is same 13.32, but C2 is 6 farad. So V2 would be 2.22 volt. Correspondingly, V3 will be Q3 by C3 and it comes out to be 2.66 volt because C3 is 5 farad. So together if you add this V1 plus V2 plus V3, it has to be equal to 6. Okay, that's how it will get distributed. So you can see together if I add them 1.11, 2.22 and 2.6 together, I add them, I'll get it as 6 volt. So this is how the charges and the potentials get distributed in series circuits for capacitors. The next analysis would be for parallel circuits. So please make a note of it before we proceed further. Okay, I believe you have noted this down, and the concept regarding the problems which can be asked for capacitors in series is very clear to you now. So we have discussed two types of problems along with the concepts. One was the problems on parallel plate capacitor, and then the second one was the capacitors in series. Okay, let's proceed further. Now let's talk about the parallel capacitors, basically parallel connections. Okay, similar type of problems, but now here the capacitors are connected in parallel. So here comes the question for you. Total volt is 12 volt. C1, C2, C3 are different. They are connected in parallel. They want the total voltage gain in the circuit. Then they say what is the total capacitance of the circuit, which we would be solving with the help of the formula. Straight away we will add it. C1 plus C2 plus C3. Then the third question they say, what is the total charge stored in the circuit? Okay. Then obviously here the total charge stored in the circuit can be worked out after finding out total capacitance. Fourth question they say, what is the voltage across each capacitor? The voltage is going to remain same, but the charge won't remain same, because this is a parallel connection, if you all remember. The fifth part of the question is, what is the charge stored on each capacitor? Okay, so now we are going to analyze a parallel capacitor circuit basically. So please make a note of this problem before we proceed further. Yeah, hopefully you have noted this down, friends. So capacitors in parallel is the topic of analysis now. Okay, let's move ahead. The total voltage gain, friends. Total voltage gain, if we talk about, it's the same thing, 12 volt straight away. Total capacitance, second part of the problem. Add them, C1 plus C2 plus C3, and you get this as 12 plus 6 plus 5, that is 23 farad. Total charge stored will be total capacitance multiplied by total voltage. So that is 23 into total voltage is 12. So that is 276 coulomb. This is the total charge stored. So the three parts of the questions are answered. Now we will move ahead towards the fourth and the fifth part in the subsequent stage. Please make a note of this before we move ahead. Believe you have noted this down. So let's proceed towards the fourth part of the question. In fourth part, what are they asking? What is the voltage across each capacitor? Obviously, it has to be same because it's a parallel connection. So whatever was the voltage across, total voltage, it would be same across every capacitor. So V1 also you will note it as 12, V2 will be 12, and V3 also will be 12. This is the fourth part of this solution for the fourth part of the question. Please make a note of it before we discuss the solution for the fifth part of the question. Okay, I believe you have noted this down. Now, when it comes to fifth part, here you can see the total charge stored will be obviously Q1 plus Q2 plus Q3. Now, from the basics, we know Q would be given by C into V. Correspondingly, Q1 would be C1 V1, Q2 would be C2 V2, and Q3 will be C3 V3. But V same across all the three, 12 volts you can see. Only what changes is the capacitance. So correspondingly, Q1, Q2, Q3, the values would be 144, 72, and 60 coulomb. So together you add them, you will find it total charge equal to 276 coulomb. You can see. Total you add it, you get it as 276 coulomb. This is how the charges get distributed across capacitors in parallel. Okay, so please make a note of it. Okay. Now, not necessarily only, you would get problems where the capacitors are only in series or parallel. At times, there can be a combination together. Some may be in series, some may be in parallel, and then we have to work out certain things as per the problem demands. So we are going to work out certain problems in that direction also. So let's proceed then, friends. Hopefully, you have noted this down. Okay. So what is important to be noted over here, for series capacitors, the charges would be same, and for parallel, the charge gets distributed. Second point of difference, voltage for parallel voltage would be same, for series voltage gets distributed. Formula for parallel, you want to increase the capacitances, connect them in parallel. You want to decrease it, connect it in series. Okay. Formula applicable for series and parallel, the same basic formula, Q would be equal to C into V. So please make a note of this slide before we move ahead towards a problem on combination type of circuit. Yeah, I believe you have noted this down, friends. So let's proceed further. Yeah. So here combination type of circuits. So here two series capacitor in parallel with the third capacitor. Okay. So let's understand this. So here you can see two series capacitors, 4 microfarad and 3 microfarad, and together they are in parallel with C3. Now the same set of questions: what is the total voltage gain? What is the equivalent capacitance of the circuit? What is the total charge stored? What is the charge across each capacitor? And what is the potential difference for each capacitor? Please make a note of this. Let's try to analyze this problem. Okay, hopefully you have noted this down. So let's proceed. So when it comes to total voltage gain, the value would be the same, 9 volt you can see. Total capacitance, if you want to work out, first for 1 and 2, you would apply series formula. So when you apply series formula for 1 and 2, you get C for 1 and 2 as 1 upon 0.583 microfarad. So when you simplify it, so C for 1 and 2, that means capacitor number 1 and 2 which are connected in series will be 1.71 microfarad. Now this resultant would be in parallel with C3. So C1, 2, 3 if I want, so that will be C12 which is 1.71 plus C3 that is 5. So together the total capacitance comes out to be 6.71 microfarad. Okay. The third thing what they are expecting is the total charge stored. The total charge stored would be whatever is the total capacitance of the circuit multiplied by the total voltage gain. So total charge, total capacitance we have worked out is 6.71 microfarad multiplied by 9 volt. That comes out to be the total charge equal to 6.39 microcoulomb. Please make a note of it. Then we discuss the fourth and the fifth part of this question. Yeah, hopefully you have noted this down. So let's proceed further. Let's discuss the fourth and the fifth part of this solution. Okay. So in fourth question, fourth part, what they ask is, what is the charge stored on each capacitor? So first of all, you need to know what is the charge on this section and this section. And whatever is the charge on this section would be same for C1 and C2. Why? Because they are in series. So let's work it out. Okay, so Q1 and Q2 will be same because they are in series. So for Q1 and Q2, I can put the formula C12 multiplied by V12. But V12 is 9, right? And C12 we have worked it out, 1.71. So multiply it and then you get the charge on 1 and 2 as same, and that is equal to 15.39 microcoulomb. Why same? Because they are in series. All right. So together now whatever is the charge on, what's the charge on C3? So for C3, Q3 will be C3 into V. So C3 is 5 and V3 is 9 microfarad. sorry, 9 volt. So 9 into 5, it comes out to be 45 microcoulomb. We get the value for Q3 also. Please make a note of it. This is the fourth part of the solution. And then we will work out the fifth part of the solution. Yeah, hopefully you have noted this down, friends. So let's proceed. Next, fifth part. What is the potential difference across each capacitor? We all know V3 is 9. Why? Because whatever is the potential across the total circuit would be the potential across C3. Therefore, V3 is directly 9. We know that. But what about V1 and V2? So V1 will be Q1 by C1. So we know what Q1 is. We know what C1 is. Correspondingly, we get it as 5.13 volt. V2, if you talk about Q2 by C2, we know what Q2 is. We have worked it out. And we know what C2 is. Okay, so just put the values, you get it as 3.85 volt. Together, you add them again, you will get it as 9 volt. Okay, because if this is 9, this branch also is subjected to 9 volt only in totality together. Please make a note of it before we talk about the next type of topic. Okay, I believe you have noted this down. Now the concept can be other way around. You can have two parallel capacitors in series with the third capacitor. Okay, so let's have a look at that. You can see now. Here we have two parallel capacitors and together they are in series with 5 microfarad, that is C3. Again, the same set of questions if you observe. The first one is what is the total voltage gain in the circuit? Second one, what is the total capacitance of the circuit? Third one, what is the total charge stored in the circuit? Fourth one, what is the potential difference for each capacitor? And what is the charge stored on each capacitor? These are the 5 sets of questions which we need to answer for this type of connection. Now let's try working it out. Okay, please make a note of it before we try discussing this. You can consider this as the final question for the day. Okay, hopefully I've noted this down, friends. So let's move ahead. So here you can see when we are talking about C1 and C2, they are in parallel. So together just add them. So C1, 2 will be 7 microfarad. Okay, so together this 7 and 5 are in series. Just put it 1 upon 7 by plus 1 by 5. You get the resultant capacitance as 2.92 microfarad. Total voltage gain as per the first part of the question will be the same as the battery voltage, 9 volt. The total charge stored will be obviously total capacitance, that is 2.92, which we have worked out, multiplied by the total potential, 9. So we get the total charge stored. So the first 3 steps are very general and common. Okay, so make a note of this. Then we'll try working out the fourth and the fifth part of the solution. Okay, hopefully you have noted this down, friends. Let's move ahead. So here was the fourth part of the question. What is the potential difference across each capacitor? Now here Q3 will be C3 into V3. So V3 can be written as Q3 by C3. So you know Q3, you know C3. Okay, so Q3 is worked out the total charge, right? 26.28. That will be the charge across this. Divided by 5. So we get V3 as 5.26 volt. Now obviously V1 and V2 are to be same. Why? Because they are in parallel. Alright, so that will be whatever gets reduced because of this out of 9 will be the potential across these two. So let's say V1 and V2 would be V total minus V3, friends. So 9 minus 5.26, that is 3.74. So 3.74 volt will be common across C2 as well as C1 because they are in parallel. So please make a note of this before we move towards the fifth part of the question. Okay, hopefully you have noted this down. Let's move ahead then. What is the potential? This is the fifth part of the question. Just make that correction. So what is the potential difference for each capacitor? So V3 will be Q3 by C3. We know the total charge. Okay, so it's Q3 divided with this. Okay, so other way around also we can work it out. Okay. V1 and V2 obviously we have worked out as 3. Now what is the potential difference for each capacitor? They are saying. Okay, so we have worked out for V1, V2, V3. All right. So for 1 and 2, what would be the potential difference? If you want it other way around, it will be total charge across 1 and 2 divided by. So here also when you solve it, 26.28 is the total charge divided by the combination of these two, okay, in parallel. So 3 plus 4 is 7. So this also comes out to be 3.75. So they match, the values match. That's what I'm trying to tell you. Either this way or other way around, you can work it out. Please make a note of this before we move ahead. Okay, now let's talk about what's the charge stored on each capacitor. This was the fifth part. Okay, so charge will be given by C into V. So Q3 is C3 V3. So C3 we know it's 5 microfarad and V3 we have worked it out. So we know 5.26 volt. This is how we get Q3. Alright. So Q3 and Q total is same. Okay, approximately 26.28 microcoulomb. This is. It has come out to be same, you can see here also. But Q1 can be worked out as C1 into V1. So we know what C1 is, 3 microfarad, you can see. And V1, we have worked it out, 3.75. 1 and 2, it was somewhere around 3.74 with decimal, with some digits there on it. In totality, it is 3.75. So we can work out Q1 as 11.25 microcoulomb. Q2 can be worked out as C2 into V2. Okay, so again we know C2 is 4 microcoulomb and V is 3.75. So it gives us 15 microcoulomb. This is how you're supposed to work out the charge stored on each capacitor for this given type of combination, friends.